I like to share one feature of nlmixr that I'm really happy with and really excited about. It's called model piping. In the tidy universe, you can modify data sets by what's called piping. Use a pipe operator to perform operations on the data set. So we extended this idea to allow what's called model piping. So first, we're going to cache these models so this will run a little bit quicker. We'll talk about the piping. First, we're going to look at the Theophylline dataset and the Theophylline model that was included in your setup script, and it's something that is typically run in a lot of examples. It's almost like the hello world of modeling. So this basically has a one compartment model with Ka, Cl, V, and eta is between log normal between subject variabilities for Ka, Cl, V with the additive error and a standard deviation of 0.7. Here we specify the between subject variabilities as log normal, and here we specify the ODEs. And then afterwards, we specify the concentration of the plasma is center divided by V. And this plasma concentration is modeled by an additive error with the additive SD estimated above. So let's just evaluate this so we can get this model up and running. First off, we want to, of course, run this model. Often in the case of modeling, we want to try other things. Of course, in this nlmixr example, you can see the objective function right here. You can see it's using FOCI and the parameters. But what if we want to do something different? Often in other places, we copy the model and modify it. But here we have some initial way to do this. What we can do with model piping is change the model in certain ways. For example, you might want to change the parameter estimates before running or after running a model, fix a parameter estimate, or do other things like change model behaviors, dropping things. So let's just start by changing an initial estimate. Right now, we're going to be using this model we just fit, change the initial estimate to 0.5, and just running a post hoc estimation, which means everything that's there will be used, and then empirical Bayesian estimates will be produced post hoc. So once we do that, what we can do is we can switch to the source code here, and we can change this to be a runnable example. I can't remember why this was turned off. It allows you to then look at that example one and run it. So here we're going to run it. Takes a little bit of time to run the post hoc estimate. Once the post hoc estimate is complete, it'll print it out in the standard R markdown way, and you can see when we looked at the parameters, the TKA is actually at this 0.5 value, and everything else was fixed. So once this is done, you can also look at fixing TKA to 0.5 and re-estimating the full model. Once that happens, you can see instead for this par fixed, everything's re-estimated, but this value is fixed. The key here was adding this fix around the 0.5. What we can do here instead is we can also fix the value to what was estimated. For example, we start with the 0.5 model that we were looking at. We say I and IA equals TKA equals fixed. Then with that information, we can then look at this par fixed Here you see that there's no standard error because this is fixed, and the value that was estimated is 0.45. That's what was piped and run. Last example is we can change the original value to 0.7 and then re-estimate. So this just gives a different path of the model. You can use it to assess sensitivities quite simply. This is something that I would say would probably be useful in many places. So all those things are about changing initialization block. And this is the initialization block we're working with. Anything that's already in there can be changed. What we're hoping to do is also change model features. So one of the things you can do when changing model features is just look at the model lines and changing certain things about them. For example, in our original model, way up here, we have this Ka is assigned to be exp tka plus eta ka, right? So if we didn't want that any longer, we could remove it. We could say that there's no eta ka on this ka parameter. So what we would do is we would take the original fit, model it saying ka is modeled by exp tka, we just change the line, and then we re-estimate it with FOCI. Let's just run this. You can see in the omega block most clearly that there is no eta ka in this model any longer. And you can see the eta ka doesn't have any CV percentages anymore because there's no shrinkage because there's no etas there any longer. So this allows you to add and subtract, say, etas to your models pretty simply as well. Or you can, this is just an example where we're adding back the Ka from that single model that we looked at. And again, we look at the omega, you can see it was added back at the end in this case. And you can see that it's not the same parameter name as BSVKA, which is what we named it in here. And here we did two different steps. First, we modeled it with this BSVKA. And then we changed the model estimate. By default, this becomes 1 when we add it to the model, but we may not want that, so we changed it to be BSVKA is equal to 0.1 to change initial estimate there. The previous printout, you can see it. You can also see it by simply printing it out here. The question becomes, how does it know where the model is going? Does it know how does it know it's a population effect? How does it know it's a covariate? How does it know it's a fixed effect? So it knows it's a between subject variability if it has eta, PPV, PSV, IIV, BSV, or BPV, which have been used for between subject variability for different types of modelers. So these are all supported as something that will assign it to a between subject variability. Thetas start with TV typically or T, and those will be assigned to population values. Things within the error structure are assigned to population values. Everything else is assumed to be a covariate. So here is an example where we're going to start adding a covariate effect. Here we're looking at this weight 70. So we're just going to be looking at our fit. We're going to pipe it with this clearance saying this exp TCL plus eta CL is weight divided by 70 x to the exponent of covariance weight power, which we typically put to 0.75. So we just change this power to be a fixed component of 0.75. And we're also going to change this TKA to be fixed to 0.5. We'll run this, and you'll be able to see that we have in the fit object, you can see it's fixed here, and it's giving you the information that we're looking at. Last thing we're going to do is change the residual errors. We'll do that by changing this to drop the 0 DVIDs that are on observations. This is typically not something that's seen in modern data sets, and it makes it so the proportional error doesn't run exactly correctly. So what we do is we assign this data set and then change this to be 0.0150, which is below all the data. And then we have the additive proportional error model. We'll just pipe it with this model statement. And instead, here we're saying it's additive error and proportional error. We changed initialization to this proportional error of 0 to 0.1. This is something that we should probably do because it assigns it to 1 by practice. And then we run the same model with the FOCI using this new data set. Once we do that, we can see that the parameters are located in this par fix block, which is right here. Now we have an additive error and a proportional error. Thank you.